Hey folks, in this video we're going to be looking at building a basic in-browser pixel editor with undo and redo. We're going to be using Rust, compiling to WebAssembly, and a bit of JavaScript. This is based on a side project going on at the moment, which has been my first opportunity to play around with Rust and WebAssembly. I'm really excited about WebAssembly for a number of reasons. Firstly, the performance aspects. It opens up the possibilities of what we can do in the browser. Secondly, that it doesn't even have to be in the browser. It'd be very interesting to see what people do with the WebAssembly runtime in other situations. And thirdly, that it seems like quite a natural compile target for a number of languages that we don't normally get to use in the browser. So in this situation, I'm getting to use Rust, which is a fantastic language with a great type system, and I'm getting to build a web app with it, or parts of a web app with it. And that's really exciting. I have to say, though, that I'm not a Rust expert, so if there's anything I'm doing wrong in this, or anything that's not ideal, please comment below to help me and the other people watching this video. Let's take a look.
Okay, I'm in an empty folder here and we're going to use the Npm Init functionality to set up the scaffolding for our project. So I wasn't aware of this functionality before, but it turns out if you run Npm Init and then some kind of package name afterwards, it will go and find the package name corresponding to what you've written with create dash appended to the front of it. You can see down here as well, so they'll do create dash and then whatever package name you've given it, and then it runs the command, the main command from that package, which is designed to do the kind of setup for you. So in our case, we're going to run npm init rust webpack, and that's going to go and run this create rust webpack package, and that uses it's going to set up a template from this rust webpack template GitHub repository. So ultimately what we get is everything that's inside here kind of processed through whatever sort of templating language they have, and that's going to set up our project for us. So if we go back to the shell and run npm init rust webpack and then editor, this is going to set up a directory called editor using that rust webpack template that we saw before. Okay, so this has set up everything we want inside an editor directory. If I now run npm start, this is going to get the whole web server going. It's going to take us across to the browser initially, but we're actually just going to come back and have a look at everything it's building. So at the moment we can see that it's compiling with Cargo and the Rust compiler, a bunch of the Rust dependencies that have been pulled into this project. If we jump back across to the browser, we can see that, well, it's hard to tell, but we can see that it actually has loaded. We can see a title in the tab, the browser tab there, but there's actually very little page content to work with, so we shouldn't be too surprised that we're not seeing anything yet. If we come back and have a look at this project in a new tab, we can see that we've got a JS folder and a source folder and this static folder. These are the main things we're going to be interacting with. So we've got our initial HTML setup, we've got our lib.rs, which is going to house all of our Rust code for this exercise, and then we've got our index.js, which is where we can kind of access the Rust classes and things that we've been implementing and use them from the JavaScript side in our little web app. If we clear this and then have a look at our index.js file, we can see that it's importing this package index.js file. So the package index.js file is a product of the build system. We don't need to create it manually. The Rust code is going to be compiled into a set of files, including WebAssembly files, which are ultimately accessed through this package index.js. And this import that we're doing here is a dynamic import. So it's not a kind of full top level ES6 or TypeScript module import. It is a dynamic import that can happen at runtime, and to the best of my knowledge, you can only import WASM files dynamically. So you need to do one of these dynamic imports to access the compiled result of our Rust code. So the first thing I'm going to do is to wrap this in an async function just to make it a bit easier to access the result of this import. So if we do async function, I'm going to call it main because I've spent too much time writing C++. And then we can just say our lib is equal to the awaiting the result of this import. Now we don't really have anything in our Rust code yet. We can open it here. It comes with, this is the result of the scaffolding, and what this is set up. We actually don't want a main function in the Rust for the project we're going to be doing, so we can delete this. I'm going to leave these here for the moment, although I don't need the console one. I'm not entirely sure what this does, so I'm just going to leave it to be safe. And now what we'd really like to do is write some code in here that we can then start to access from the JavaScript side. So we're going to set up a image struct, something that's going to contain all of our image data for this project, and we want that to be accessible from the outside. So we're going to make a public struct called image, and we're ultimately going to have an implementation for it as well. And the implementation for the moment is going to include a new function that is going to return an image, and it's just going to be an empty image. This is obviously very basic. It doesn't do much because there's no content in this class or actions we can do on it. We can just make new ones. But in order to expose this to the JavaScript side, we need to add an additional, I'm not sure what they're called, perhaps a directive, something a bit like this up here. And we're going to add wasm bindgen here and here in order to get that exposed up to the JavaScript side. So if we try and compile this, I'm just running kind of cargo check in my editor, making sure this all goes through smoothly. It doesn't use the same build cache as the other one, so this is going to take a moment. It seems more or less happy. There's a small error we can correct, but it seems okay. If I check the Webpack dev server, that also looks okay. So this is quite promising. If we want to access this, we can now say an image is equal to lib.image.new. This is how we can call into that new method we've just defined in Rust. Again, this isn't really going to do much. It's going to give us this image class and not much else. We can sort of log this to see how it might be, and if we run our main function down here, make sure we're actually running our code, and pop across to our browser tab, we can see, hopefully, that it's reloading, and yes, it's outputting this object pointer, which is how Rust objects appear on the JavaScript side. We're just sort of keeping a pointer to the memory, like, I don't know, the whole WebAssembly setup is managing that, and that's how it likes to represent things. Now, one minor thing we can tweak here is that this is not the normal way of making classes in JavaScript, or making instances of classes in JavaScript. We would normally expect to do this instead, and the Rust bindgen setup has a way of doing that. So we can take this directive and add constructor here, and this does the necessary tweaking to make sure that it's exposed in the correct way, and this should still be printing our little pointer as expected. So that's nice. Of course, in order to draw this image, we want something to draw it onto, so we're going to set up a canvas. We're going to open up our index.html and add a canvas element in here. I'm going to make it 500 pixels wide and 500 pixels or units, I'm not sure how it works exactly, high. We need to close the tag and give it some kind of ID so that we can access it easily. With that in place and lined up, we want to have a draw function, essentially, which is going to draw information to this canvas. So we're going to draw it. We're going to draw, maybe with the image initially, although we don't have much image data to actually draw yet, so we're going to come back around to that. But we're going to pass through the image for the moment, and then we're going to say that our canvas is equal to document get element by ID and our my canvas ID that we added. So we have our canvas. From that, we need a context to do anything with a canvas sort of graphics element, and we say canvas.getContext and ask for the 2D context. And from here, we can start drawing things with this. So a very basic idea might be, and we're going to remove this very quickly, but just we can check that it's working. We can draw a rectangle from 0, 0 to 50 by 50, and it's going to be red due to that fill style. So if everything's working, we get a red rectangle, or square in this case. But that seems hopeful, so we know we've got a canvas here, we know that we can draw onto it, and now we can look at improving this. So as we're implementing a pixel editor, it might be quite nice if we could see those pixels. So we want to draw a kind of grid onto our canvas so that we know what we're interacting with and what squares we want to edit as we go forward. So we're going to comment this out for the second, and then set our stroke style to just be black for the moment. Context.line width, just 1 for the moment. And then we need some concept at the moment. We're going to change this soon, but the height and width of our grid. So we're going to start with a 10 by 10 pixel grid, and each of our cells is going to be a 50 by 50 block, essentially. So we can now draw, have a loop to draw all of our lines. So we've got x less than width for the moment, and x plus plus. And in each of these loops, we're going to want to draw another line. So we can say we want to begin a path, and we want to move to the start of the line. So the start of the line is going to be x, because as we go across the width, we're drawing the lines which are the full height. So it's going to be at x times our cell size and 0. And we're going to draw a line to x times cell size all the way down to the full height, which is going to be the height times the cell size. And then we do context.stroke in order to actually produce the line. And then we can repeat all of this for the other line. So we're going to go y, y, height and y. And then we want to move initially to 0, the start of the line, and at the correct height, which is going to be y times cell size. And we're going to finish at width times cell size, which is the end of the line, and the correct height, which is also y times cell size. So if we save this and have a look at our browser, we can see that we have a grid now, which is nice. It's missing the ends because of somehow the way that canvases work. You need to kind of shift the pixels around a little bit in order to get it working perfectly. We're actually going to move these all by plus 0.5 because that gets us sharper lines that look a little bit better. I've really no idea why the Canvas API is designed in this way, but these do look sharper as a result. And in order to get those final lines at either end, at the right and the bottom, we're going to, actually we need to fix this. We need to go up to the sort of less than or equals instead of just less than. And we also want to bump this up by 1 pixel just so that we're not going over the edge. And that should give us a nice grid for drawing our kind of little pixel art on. We now want to draw some pixel data on here. We don't have any pixel data yet, so let's go about setting that up. One of the first things we can do is, instead of kind of hard coding this here, we want to make the width and the height kind of properties of the actual image. So it'd be much happier if we were sending them in here and then extracting them here. That would be a better kind of storage for our data. So how might we do that? If we go and have a look at our lib.rs, we want to introduce width and height values in here. Now, in JavaScript, you only have a number type, basically. It's all integers and floats are represented as a single type that you might refer to as a number. In Rust, it's got a much wider range of integers and indeed floats to work with. Here we want to use an integer referred to as a usize. That's the best thing that suits our future usage of this. So we're going to have 2 fields on this image struct called usize. We're then going to accept 2 arguments to this, if I could type, both of usize, and we're going to put these in here. Okay, so that's going to allow us, and the compiler, the whole setup here with Rust and WASM is going to automate the process of making these 2 values passed in here. become the arguments here. So that's all taken care of for us, which is great. We can then extend this saying we want to have a way of returning the width here. So this is going to return uSize, and it's just going to be self.width, which means we need to give it a self to access. And we can do the same for the height. So these two then become these two accessors that we're seeing up here. So this should all work smoothly. This continues to, yes, display the grid. So everything seems to be okay for the moment. With that width and height information, we can now start to populate an array of cells within the image data. So we might say that these cells are a vector of RGB values, and RGB we'll have to define ourselves. I'm sure there are plenty of ways of going about this, but this is our current preference. So we're going to do it very simply with kind of 0 to 255 RGB colors, which are well represented as U8. And this means that our image is going to store a single dimensional vector of all the RGB values. So we are going to compress this kind of 2x2 grid into a single vector, which means we're going to have to do some kind of lookups to get from our width and height and sort of X and Y coordinates into the cells, but that shouldn't be too hard. What we can do here now is say that we want our cells to be, and we're actually going to, we create a new vector and then we're going to resize it because the Vec API, as far as I can tell in Rust, doesn't provide you with a way of creating a new vector of a particular size. In order to resize it, it has to be mutable, but we can now say we're going to resize this to something with the width times the height, and the value we want in every single one of these slots is going to be a mid-tone blue. That's what I'm going to choose. So if we say 200, 200, and 255, this is going to give us something that's a kind of light blue, and we can add cells in here, and hopefully that is going to compile fine, which it isn't. So it is expecting a semicolon at the end there, and also it expects to be able to kind of clone this into the array in some way. I'm not 100% up to date on exactly all the ins and outs of how Rust manages the data, but I do know that if we add clone here, then that should work. Okay, so it's warning us that we're not actually accessing the cells yet, but it is otherwise happy with this setup. So we do want it to give a way of getting to these cells and to passing them back to JavaScript. So if we add a method like this, again, it's going to require the self, and it's going to return a vec of these U8 values.
I'm going to jump in here to say that I'm about to very confidently tell you that you can't move anything except for numbers and arrays of numbers in between JavaScript and Rust. This is just wrong, not in the least, because as you can tell, we've already moved an image pointer back and forth, but there are pages of docs about how to move values of different kinds in between these two levels, and it's possible to tackle in a number of different ways. What I can tell from looking at it, though, is that moving a single RGB value is sort of very simple to do. Moving a vector of RGB values might be a bit more tricky and might involve implementing some traits, which is beyond my current kind of experience level with Rust. But all I can say is there are different approaches to doing this. Some might be easier, some might be more complicated. For the moment, we're going to kind of convert it all into a single U8 array, and you'll see how that goes. But you've been warned, some of the statements I'm about to make aren't quite correct. I need to do a bit more research. Maybe in the future I will get a better hang of it. Thank you.
So we're limited in the ways in which we can pass data from Rust to JavaScript and back again. Basically, it all has to be numbers or arrays of numbers. If we pass this vector of U8 values out to JavaScript, it can happily become a uint8 array objects. Like JavaScript these days has these numerical array objects, which are, I guess, more tightly packed numerical data than if you use a kind of a standard array and just throw number values in there. So we can deal with kind of non-nested arrays being translated quite easily, along with plain values being translated quite easily between Rust and JavaScript, but we couldn't do something like send a vec of RGB values out. because it wouldn't really know how to do that, and I don't believe it can anyway. That's the principle I've been working with. We also couldn't do something like a double nested array of arrays of U8s, where maybe each of these inner arrays are only 3 elements long. We can't do that either, unfortunately. So we're going to have to flatten it all and do some indexing on the JavaScript side to get it correct. So we want to get from this array of cells into some kind of single array of vec8. So we want to maybe flatten these RGB values into arrays of their own and then concatenate them all together. And we can do this by iterating over all of these RGB values. We can pull out each one and create a new vector of these, so rgb.r, rgb.g, and rgb.b. I'm not an expert in the kind of memory usage here. Maybe there are smoother ways of doing this, but this is how I've come across it at the moment. We're then going to collect up this iterator of values into nested vec8s, vec u8, and I think we need an operator here, and then we can concatenate all of these things together. Oh, and return it, so we don't want that final semicolon. So we start with our initial array of RGB values, we iterate over it, and for each one we're going to replace that RGB value with a little vector of U8. So we now at this point have an iterator of vec U8. If we call this collect, we are collecting all the values from this iterator together into a kind of nested array where there's vec U8 inside another vector. And then when we call concatenate, it's going to concatenate all of these nested values into one great big long array. So we now should have a vec U8 array where there are 3 times as many elements in it as there are cells. And this is because each cell here has become a RGB element in the final array. We're just going to see if this compiles. Okay, so it wants us to add the copy trait here as well. Again, I'm no expert. I hope this is reasonable without being egregious. I'm sure there are some sort of tweaks that could be applied to make this a bit more efficient. But essentially we should now have this cells method, which is going to provide all of the values back up to our JavaScript layer for us to interpret and draw. So if we go back to JavaScript, we want to draw them all before we hit this set of lines. So we draw the lines over the squares to make sure the lines are nice. We can say that our cells are the result of calling image.cells, and then we're going to do, I guess, a double nested loop. So we're going to go from x equals 0 to x less than width, incrementing again, and the same thing for y. And we're going to be able to say that our index is going to be y times the width plus x. That's going to take us to, that would index into an array that was the same length as the number of cells, but we're going to have to take all of this and multiply it by 3 in order to get to that first R of the RGB of each cell. So if that's our index, we know that our color is going to be set by that, so we can construct our own kind of color doing this. Again, maybe there's a more efficient way, but we can use string interpolation, and we can say that our cells indexed here plus 0, which is redundant but makes the kind of whole logic flow a bit more clearly. So we can now index into the 0th, 1st, and 2nd colors there in order to build up this RGB string value. We can now say that our context.fillStyle, copying what we've got in that comment up the top, is now the color, and our fill rectangle is going to be dependent on where our x and y are. So we're going to start at x times cell size, we're going to, and y times cell size, and we're going to draw something which is cell size, if I could type, by cell size. And if we save all of that and we come back and have a look, we can actually see that this is drawn out a nice light blue grid and appears to be working well. Excellent. Right, now it's not much of a pixel editor if we can't edit any pixels. So we want to have a look at what it's going to mean to set up some kind of a brush tool here so we can change the color of each pixel. So how might that look? We would want to set up some, if we get rid of that for the moment, set up the canvas to have some event listeners on it, so it's aware of our mouse interactions. So we've got our setup canvas. Oh, we're taking an image. We're going to fetch the canvas the same way we did up here, and we're now going to say that canvas, we can add an event listener. Again, if I could type, I'm going to look out for the clicks, and on each event we're going to process that in some way. Now I'm going to paste in some code I got from Stack Overflow. We have the canvas already here actually, so we don't need this line, but we can say this is essentially getting the total size of the canvas on the screen, and then it's comparing so client X is the mouse position where we've clicked, and it's comparing the mouse position where we've clicked with the top left coordinates of the canvas, and it's allowing us to derive an X and Y position within the canvas itself, which is going to correspond to kind of what pixel we're clicking on. So this is going to give us a sort of screen pixel value. When we divide by the cell size and floor it, it's going to give us a coordinate in our own pixel space in this kind of 0 to 10 X and Y pixel space. Of course, the cell size is only going to work if we, for the moment, move this up to the top level. There are other ways of managing that, but it's the easiest thing to do for the moment. And so we now have a X and Y here, and we want to do something like image.brush with X and Y and some value, color value. At the moment, I'm just going to hard code this to a green, so a similarly kind of light shade of green. And then because we've made a change to the image data, we're going to redraw it so that it's fairly visible. So this should work, but of course we need to implement this image.brush function. So if we come down here, we can say, let's provide if brush, we're going to edit it, so we need a mutable reference to self, and we're going to say we've got X, which is a U size, Y, which is a U size, and then a color, which is a vec U8. And this isn't actually going to return anything, it's just going to edit the internal data structure. And we're going to say that our index, as we've seen before, is going to be Y times self times the width plus X, and this is going to allow us to figure out which cell we want to change in our cells array, and we're going to change it to be a new RGB value where R is color 0, G is color 1, and B is color 2. And if we check that that compiles, it seems to. We can come back, we're going to assume this is working at the moment, and if we come back to test it, every time I click, the pixels turn green. So that's nice. We can't change them back, we can't undo, redo, we can't choose a different color, but that's a good step forward. To take this a little further and to allow us to choose the color, we're going to introduce a bit more of a kind of state wrapper within the JavaScript code. So instead of just having an image here that we're going to pass around, we're going to want to set up some kind of state. Maybe there'd be a better name for this, but it's okay for the moment. And this state is going to include a current color that we're painting with. So I'm going to set it to that green that we've used above, and I'm going to pass this state around instead. So everywhere that we have been passing in our image, we want our state, so we can say const image is going to be equal to state.image, and then we can brush on that still. We've got the state passing in here, state passing in here, and up here const image equals state.image. This means we've got a nice place to hang our current color and to update our current color if we want to. If we just go and check that this is still working, it is, which is nice. and we can load up the HTML and think about adding some buttons that allow us to change the color of our paintbrush, essentially. So we've got some button with an ID, and we're going to make 3 of these to give us a very simple palette to work with. And when we come back, we can add more things in here. So if we do document.get element by ID, and we're going to look for the red one first, and then we're going to add a event listener for the click event. And I mean, it's worth saying that, you know, if this was a big serious project, I wouldn't necessarily be, you know, doing handwritten HTML and sort of JavaScript. You know, always good to reach for React or some other toolkit. I personally really enjoy Elm. But you know, I'm trying to keep this as relatively streamlined as possible in certain ways. So if we've clicked on red and we've got access to state in here, we can say that now our current color, if I could type, is now going to be a delightful shade of red instead. And we can just paste this out a couple more times, saying if it's green, then we can change it to our green, and if it's blue, we can change it to a comparable blue. So if we come back here, we've got our red, green, and blue down here. If I click red, that is not working, which is fair enough, and that is because up here we have still got our hard-coded color, which I should have noticed before. We're going to use our current color instead. So this is going to reload. Initially it's set to green, but if I click red, we get red instead. If I green, we come back to green, and if we go to blue, then we sort of looks like we're erasing it, but we're painting over with blue. So that's working. We can change our very simple color palette here. There's another step. It's a little bit more satisfying if you can drag. So at the moment, if I click, it doesn't really do anything, I'd guess. Yeah, there you go. It appears at the end of the drag, but that's about it. It's nicer if you can paint in these tools by pressing down and dragging around. So we can look at what it might take to add that. We're going to want some kind of drag state. So initially we're not dragging anything, but then we can say back on this canvas, we can say on a mouse down, we want our state.dragging to be true, and on a mouse up, we want it to be false. So this means at the beginning and end of each drag, we should hopefully have the correct state. And then we can look at another function very similar to this, where we can say on a mouse move, we don't want to do anything if we are not dragging. So if we're not dragging kind of in drag mode at the moment, i.e. we're just moving our mouse around on top of the canvas without having clicked, then we just want to exit and do nothing. But otherwise we're quite happy to continue with the same logic. And I guess, you know, I should probably extract this and share it with that function above if I wanted to be a bit cleaner, but for the moment the copy and paste should be fine. If we click over here now, if I click and drag, we can see that that's working reasonably well. I imagine there's lots of little things we could fix about it, but it's a good start. Okay, so the final chunk we're going to add here is a kind of undo and redo. So this is a nice thing in any graphical editor, or indeed any digital tool at all. You always want to be able to undo mistakes. And it's interesting to look at implementing undo in different ways. Quite often, I think the two I've come across are to use some kind of command pattern where you encapsulate every change as a command object, and that object is able to kind of do and undo the change it is responsible for itself. You store these objects in a kind of some array, and you kind of walk up and down them, asking them to undo and redo as requested. The other option is that you can reach for kind of, well, I'm going to say reach for immutable data structures, which helps to improve your kind of memory footprint. But otherwise, even without those, you can just remember like the entire state before and after every interaction, and then in order to undo and redo, you just walk up and down this kind of array of states, just reusing whatever state is at that point. Now we're going to look at doing this with immutable data structures because there's a good immutable data structure library for Rust, and because that means you're going to reduce your memory footprint because a fair amount of the state is going to be reused in between different undo and redo slots. But you can approach it in different ways. So this is going to be quite a big change. We're going to start by adding the Immutable library to Cargo, which is the Rust package manager. So this is the file cargo.toml is the file that's specifying all of our dependencies. We're going to come down to here and we're just going to say we're going to use the Immutable library, which is just called im, and we're going to use version 15 of it. Fortunately, the server we're using goes and fetches and builds this for us automatically, so that's quite handy. And the first step we're going to take is to use this Immutable library in place of the current vectors we are doing. So there's going to be quite a few steps in this undo redo process, but the first one is to look at our Rust code and just use this im library instead. So if we do use im vector, then we get this data type called a vector, which is an immutable version of the vec, which is built into Rust, or comes as very much a standard in Rust. So if we use a vector instead, we then need to change our approach because this resize method doesn't exist in the same way. Instead, we're going to say we want a vector from an iterator, and that iterator is going to be us counting from 0 up to the cell size, and for each cell we're going to ignore the actual value and use this RGB value instead. So if we get rid of that, Rust is going to require, something's not working here, we need to give it a moment to build on the checking side as well. Essentially Rust format isn't kicking in, so I must be missing some subtlety here. Oh yes, it's going to be the end of this from iter operation there. Okay, that looks a bit happier. That's still going to be unhappy because we don't have this in scope, so the from iter behavior is dependent on making this trait available in the scope, so we can import this up the top in order to make that work, and when we compile that, that goes through fine. So the nice thing here, the fact that it is compiling, indicates that this interface is still allowed, so we can still iterate over all the cells, and also we can still call this when we have a mutable version of the data. So we can do mutable updates of this immutable structure if we want, but it also provides efficient immutable updates as well. So if we jump back over, we can still see that this is working, so that's great. We don't have to worry too much about everything breaking and doing a lot of work to get it back into one place, but we can now look at how to use this immutable data to make a more efficient setup and a more friendlier undo queue. So one of the things with immutable data structures is that when you do a update of an immutable data structure, then when you do an immutable update or an update of an immutable data structure, not a mutable update like we're doing here, when you do a normal update of an immutable data structure, you get a new copy of that data structure back. And that means that we would want to return a new copy of our entire image to make this work smoothly, or the way I'm planning to do it anyway. So we would update cells, we'd get a new cells value back, and then we would return a new image from this brush, and then we would manage this kind of collection of images as our undo stages. So there are sort of multiple steps in going about doing this. But the first step is going to say our brush function is going to return an actual image. And in order to do that, we can say our new cells value is going to be self.cells, and then we're going to call the update function. So this is the immutable way of updating this data structure. It returns a whole new cells vector with this one change in it. And then we're going to return from this a whole new image object. So the width is going to be, oh wow, I cannot type. The width is there, the height is there, and then cells is going to be this new cells data. And we're going to compile that. That seems to work fine. Now, we could possibly work with this in the JavaScript code. So every time we call brush, we would get a new image back and we could manage the undo queue in JavaScript. But I'm going to choose to do it in Rust instead. And so in order to do that, we're going to want to, instead of working with images in the JavaScript code directly, we're going to want to work with some kind of other form of state that has an internal undo queue to manage all of this complexity. So I'm going to make a new struct called state in this case, or perhaps internal state, just to make it different to that state object I made in the JavaScript world. It's going to have some kind of undo queue, and the undo queue is something we're going to write that takes an image. And when we implement our internal state, we're going to want to make new ones of these. So a bit like we had before, we're going to want to take the width and the height to start this whole thing off, and we're going to return an internal state, and this internal state, sorry about that, is going to have an undo queue, which is a new undo queue taking a new image. So we're going to call image here, pass in width and height. So we haven't written all of this yet, so it's not going to actually work, but that's more or less the structure. When we start this new eternal state, we're going to start it with an undo queue that begins with our initial version of the image. So what does our undo queue look like? We're going to make it parameterized because technically it could work with anything, and it is going to work with a queue that we're just going to base on being a vector of this entry type. And if we want to implement an implementation for this, we have to account for t in each case, and we're going to say we are going to expect an entry of type t. This is going to return an undo queue of type t, and the way it's going to do this is by making an undo queue where the queue is just a vector around this entry. Okay, quite a lot of fuss, but that is going to compile. It's going to complain about various things never being used, but we're okay with that for the moment. So we still have quite far to go with this. One thing we might look at is how to return the current. Oh, actually, yes, this is going to need a concept of an index as well. So for an undo queue, you can store multiple states, and then you want to be able to walk up and down those states without necessarily removing the ones you don't use yet. And so we can do this just by adjusting an index rather than by kind of pushing and popping actual states off the queue. And the fact is, like, when you undo a certain state, you want to be able to redo and return to that state. So you want to leave that state in the queue. But our index is obviously going to start at 0. And if we want, we can add a function here to return the current entry. So this is going to need self, it's going to return a t, and we're just going to return our queue, and it's going to be indexed, and we're going to have to clone this. Again, my complete understanding of Rust and the memory management isn't there entirely yet, but this does seem to be necessary and vaguely understandable given everything that Rust requires. So that's how we make that happy. So the idea here is that we're happy to return a clone of the image because the image is relatively cheap to clone. When we clone an image, we are cloning these two size, just these two numbers, and then we're cloning an immutable data structure, which is basically designed to be cloned. So it can an immutable data structure can be cloned incredibly quickly. If we were cloning the original vec value, then it would be copying all of the memory and would be quite slow for large images and wasteful of memory. But with immutable data structures, whenever you clone it, it can just share all the memory with its previous instance because it's the nature of the data structure itself. So that's pleasantly why that works. And we can say here, if we want to get access to the actual image from our internal state, then we can, return the undo queue.current. And hopefully that should all compile. Yes, we had to run self.index at this point. Index itself doesn't exist. And it wants the undo queue to be cloned. Alright, so the image itself, despite my little speech before, we haven't implemented clone for it yet. So I'm going to say that it is clonable. It's clonable quite cheaply. It's happier with it being that way around. Oh, and not on the implementation. I am embarrassed by this. Please forgive me. Okay, so this is a lot of kind of warnings about stuff never being used, which we're okay with for the moment. So, part of the reason it knows that it's never being used is because it's not accessible from JavaScript yet, because we haven't pasted this in everywhere. And I'm going to be honest, like, I'm not sure exactly all the places we need this, and I'm not sure actually how often I need to write pub in front of these functions. So I apologize if any of you know better out there and are wincing every time I write it. But I'm now just kind of doing it out of habit, and we'll come back to this later to do better. So the other thing is we're going to be making this from JavaScript now. We're going to add that constructor line so that behaves better. And okay, this is actually telling me that I've got a bit too casual with this, so it doesn't want to. We don't need to expose those, and that's not going to. And it's going to be happier if we don't. So again, a bunch of warnings, but we can see how this is going to work when we return to JavaScript. So we're going to sort of piece this together slowly. To begin with, we want some kind of internal state created here instead. So this is going to use our internal state constructor. We're going to store that here instead. And then up here we're happy. In order to get the state, we can say internal dot and just get the image from the internal. But when we get to here, we don't want to get the image and then call brush, because that's going to just generate a new image by itself, and instead we want to manage that image generation within the Rust code. So we're going to change this to state.internal.brush, and we're going to do the same down here as well. And then we're going to come and implement that. So down here we're going to need a function called brush, which is going to look very similar to the one above. It's going to need a mutable reference. We're going to call with an X and a Y, and our color, which is going to be this vec_u8 again. It's not going to return anything because it's going to manage this extra image that's created internally. And what we're going to say is our image is going to be equal to self-undo queue.current, and then we're going to create a new image by calling brush on this image. So our image.brush function now returns a new image, so we want to capture that and push it onto the undo queue. So we can pass this through. Hopefully that should be fine. And now we want to do undo queue.push with this new image. Now we haven't implemented push yet, so we can have a look at doing that. It is going to be a mutable change to the undo queue, and it's going to have a new entry. It's not going to return anything, and we're going to say that self.queue. Now the complexity here is that we want to actually truncate the queue, and we want to truncate it to index +1. So we want to, in the event where someone's done a lot of actions, we built up a lot of data on this undo queue, and then someone started undoing those items, then they're kind of walking back through the queue. And if you want to push a new, if they then sort of make a change, we want to push a new state onto this queue, we want to truncate the queue back to where they've been undoing to, and then start adding new states on there. So we can do self.queue push this entry, and we want to set our index to just plus equals 1 for the moment. So we're incrementing our index, so we're going to reference this new entry that we've pushed. Okay, so we've still got a hangover from here. So this is still saying that brush requires a mutable self, which it doesn't anymore because it's returning a completely new image. And this seems very uncomfortable with the amount of, there's a lot of things that it's complaining are not used, but hopefully we're going to see this work all the same. So what we have is that we've got this brush function now, which is getting the latest image, editing it to get a new image, pushing that onto the undo queue. The undo queue is incrementing the index, so it references this new entry, and when we ask the undo queue for the current entry, we're going to get that newly sort of added entry there, and that should be what we get back from image. So when we return here, we should see that we are kind of doing a completely internal brush update here, an internal brush update here, and then when we're drawing it, we're fetching this state and drawing everything through. So if we come and check it out, this does seem to be allowing us to draw stuff, which is great. It's hard to tell if this is working perfectly until we start adding undo and redo, but let's give that a go now. So if we come back, we can have a look at our index.html. We can add some more buttons. It's going to include an undo and a redo. We can delete that. We can come back to our setup function here, and we can say that in the case that the undo button is clicked, what we want to do is call undo on the internal state. And if we're calling redo, we're going to call redo on the internal state. And now we have to go and implement those, obviously. So if we come back to our Rust code, this function now needs I'm going to add them here, undo code. So it's going to be mutable in this case. It's not going to return anything, and it's actually just going to pass it through to the undo queue underneath. So we're going to call undo on that. And similarly, we can call redo in this situation. We can now take these and call undo. Again, it's going to mutate itself, but it's not going to return anything. And in the case of undoing, we are just going to -1 from the index. Okay, now we want to be careful with limits here, really. We don't want this to go to less than 0. So we could say something like if self.index is greater than or equal to 1, then undoing should take us back to 0, but no further. And if we're redoing, we're moving our index forward through the stack again. So we can say if our index is less than the length of the queue, I guess less than the queue -1, then we can afford to add an index to it. So our undo and redo are very cheap here because we're just changing our reference to this point in the queue, and then this current is going to change its behavior accordingly to return that particular entry. So here we've got undo and redo, so that's linked up. This is hopefully compiling. We're getting a lot of warnings, so I assume that's okay. And if we come back here, we can make some lines, and if we click undo, nothing is happening. Of course, that's because I'm not asking it to redraw after doing the code. So here we now want to draw the state in each case. So if you've undone it, the state's going to change. We want to redraw it in order to be visible. So we can make some nice things here. And then when you click undo, okay, it's inefficient, and we can talk about why in a second, but it is essentially working back through. Obviously, I'm having to click loads, and this is because actually when I click and drag, I'm painting several times into each square, so I have to undo and redo each of those several times. If I'm a little more careful with how I do things, then undoing and redoing becomes more obviously correct. We can have a look at fixing up that drag behavior if we want, but for the moment we can see that this undo redo appears to be working quite well. The simplest way of getting this drag behavior to work better with the undo redo is to say that if the cell is already the color we're trying to paint it, then like don't paint it that color. Like don't perform an operation, don't put another state in the undo queue, so we don't have to work back through it all the time. There are other issues with dragging as well, which we might get into in a second, but that's a good place to start. And interestingly, that allows us to look at the Rust option type. So we can say that this brush operation isn't always going to return a new image. Sometimes it's going to return nothing at all to indicate that no work was actually done. So we can say that our colors equal, like the color that we're hoping to paint this is equal to this RGB, just extracting that. And we can say if our accessing the cells directly to get the color, if that's equal to our color, then actually we're going to return none. So if it's already the right color, we're going to return none. Otherwise, we're going to do this work that we've got down here, and we have to wrap our image in a sum in order to make that work. So there might be some issues in here, which it clearly thinks there are. So we can't do partial equalities on RGB values, but I'm happy to add that because the RGB is quite a simple type, so I don't mind it deriving that. Obviously, it doesn't like the fact that we haven't added color to this update function. And now we're seeing the fallout down here. So we're calling new image and we're getting back an optional image, or calling brush and we're getting back an optional image instead. So our new image we can match on this. In the case that our new image is actually none, we can just do nothing. But in the case that there's some image there, okay, we'll improve the wording here, but in case there's some image, we're going to push that onto the undo queue. So this is kind of an optional image. Oh, we can only add that semicolon if it's within a block. And we want to do that in order to make sure both of these sides, both of these options are returning the same kind of unit type. Okay, so in this case, whenever we brush, sometimes we are going to add a new entry to the undo queue, and sometimes we're not, depending on whether it matches. So if we now have a look at how this plays out, if I choose red and drag that around a bit, if I hit undo, you can see it's undoing each cell much more appropriately. Now, of course, you might expect it to undo the whole drag at the same time, and we can look into doing that too. That's an additional bit of complication, but at least this is behaving a little bit more reasonably. So as a final step, if we want to improve this drag behavior so that we undo the whole drag at once, we need to think about how we're actually managing our undo queue. At the moment, every single time we change the color of one of our pixels in our canvas, we add a new state to the undo queue. But for the drag, obviously we need something more complicated where we start some kind of larger undo block that can be undone and redone all in one go. And then we can kind of start that at the start of the drag, and then we close it at the end of the drag, and we rely on that becoming one unit. So one way to approach this is to add some kind of extra metadata to our undo queue so it understands kind of what state it's in for navigating this stuff. And we'll look at doing that now. So in the Rust code, we can add a mode concept to the undo queue. There might be better ways of doing this, but this is how I've come across doing it in the past. We can look at several different states. So we can have a normal mode, we can have just about to start a block mode, and we can have a in a block mode. So we're either kind of treating every single update as just a fresh update. We are either going to, or we're going to start a block with the next update that comes along, or we're in a block, and we would need to treat each update kind of slightly differently as it comes through. So when we are starting off, we're going to be in normal mode, which I think is pretty reasonable. And we're going to say what happens when we push. So when we push, we're going to inspect what mode we're in. And we're going to say if we're in this normal mode, then we're happy to do this kind of standard update. But if we're about to start a block instead, then we want to do the normal update, but also set our mode to be in the block. Oh, we're going to have to do mode here. And if we're in a block, then instead of doing this whole thing, we're just going to replace the current entry. So just going to use the new entry that's coming in to overwrite whatever we're currently looking at. So I don't know if this will make sense, but basically normal mode operated the way we were before. If we're about to start dragging, and this is the problem, like we click our mouse and we're kind of about to start dragging, we want to move ourselves into, like, we want to start a new block so that the first change that happens is still going to make a change, but we also want to say the next change just overwrite our current state. So this means at the end of the day, if you start a block with one state, you then have 15 in-block updates, all 15 of those are just going to overwrite the current state, and then you're going to return back to normal mode at some point. We're going to have to add a method for doing that. And that means this kind of 15 updates becomes a single entry in the undo queue, and you can move past it kind of in one easy step. So our whole drag can become one step in our undo queue, which is ultimately what we're looking to do. So in order to enable this, so we're going to have a look. Oh, it doesn't like the fact that I've used normal somewhere up here by itself. So in order to enable this, we need to think about how we're going to use it from the JavaScript side, and we'll come back here to do some further updates. So the main thing is when we're looking at dragging, we want to start, when our mouse down at the start of the drag, we want to start this block. So we're going to call start undo block on our internal state. And when the mouse is up, we're going to call close undo block, which means we need to implement these methods down here. So start undo block here, it's going to be immutable, and again we're just going to call through to here, so do something similar. And we're going to have obviously similar functions up here, but instead of doing an else, it's just going to set the mode. So our mode in this case is going to become start block, and our mode in this case is going to go back to normal. So again, we start the drag. Before we've done any kind of painting at all, we've moved our undo queue into this start block mode. That means when it receives the first brush instruction, the first update instruction, because the undo queue doesn't actually know about brushing as such, it's kind of more independent than that. When it receives the first update instruction, it's going to treat it normally, but then believe it's moving into an in block. So it's just, from that point onwards, it's going to be overwriting that state with this entry, every entry that comes in. When we finish our drag, we're going to do the mouse up, which is going to call close undo block, which is going to return us to normal. And so every new change after that is going to come in as a new entry in the queue. If we compile that, we can see that's still working, and we can come back here, click and drag, and if we hit undo, it's managing them all in one block, which is nice. So undo, 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 redo, redo, redo. And that's how we get a nice, well-behaved undo queue working with immutable data in a pixel editor written in Rust on a canvas for a little online app. I hope you've enjoyed it. Thank you.
Thank you for watching. I hope it served as a good introduction to combining JavaScript and Rust via WebAssembly and to the joys of immutable data structures and undo queues. If you want to see more, don't forget to like and subscribe. And if you have any questions or if there are any topics you'd like me to tackle in future videos, then please leave a comment below.